Hello, everyone. Welcome back. Fortunately, I had a computer issue where my internet wasn't correct, went off, and actually I lost connection. So I believe what we're talking about, and pick up from where we were, is we're talking about, remember here, we're talking about limits and infinity. And more specifically, we're talking about the behavior of rational functions far from zero. Okay, so let me start that over. So remember, a rational function, as I mentioned in the first part of the video lecture, is basically we have a polynomial on the top and the bottom. Now, this is kind of the most mathematical thing you'll see today in this video. But basically what happens is on top we have a polynomial where the x is our variable. The n's, these are our exponents. And the highest power of n is n. The highest power of the polynomial on top is n. And then the next power, if you have a next power, and then so forth down to x the first, and then the constant. And then down here, I have the same thing, or m is our highest power of the polynomial on the bottom. And then the a's up here, just numbers, the coefficients in front of the x's. And down here, the b's are the coefficients in front of the x's down the bottom. Now, what we're going to say is that what happens if you're far from zero, then this whole thing basically acts more like just this. Basically, the highest, what's called the degree, or the highest power of polynomial in the numerator with its coefficient over highest power down here with its coefficient. And so I want to show you something to kind of help demonstrate that. Let's take a look to explain that better. So let's go back to Desmos. Okay, actually, let's get rid of these functions. Let's take a look at a new function. So first off, let's just take a look at a polynomial. So 3x squared, to try and kind of convince you of this, minus 5x minus 2. Okay, it's a parabola. It's a second degree polynomial. Now, what I'm going to say is let's actually compare that. So what I mean by dominating is basically whatever degree is, the highest power kind of dominates the entire polynomial far from zero. What I mean by that, let's compare this to the graph of 3x squared. Okay. Now, you notice close to zero, they're not that similar. Okay. But once again, if we zoom out, they look a lot more and more alike. Okay. Basically, the further you get from zero, then basically the less and less these other terms matter, and the more the highest power term matters. Let me show you that another way. Let's imagine x is equal to 1,000. Okay, so another nice thing about Desmos, we can actually calculate things. So 3 to the 1,000, okay, minus 5 to the 1,000, minus 2, okay. If I just do 3 to the 1,000, let me just copy that. That's just 3 million. So when x is 1,000, it's not even that large. And basically, you can see this is 3 million. This is 2,994,000. So almost 3 million, almost the same. So as you can see, this has a dominating effect on your polynomial. And that's true of all polynomials the further you get away from, the closer or the further you get from zero, either in a positive or negative direction. Okay, so that's what we're saying. Now, let's take a look at this idea. What do you mind dominating this? Let's actually get rid of this. Let's actually change this function. Let's actually put a denominator in. Let's put this over. Oops, I should go back to that. Let's divide it by 2x cubed. Okay. Now we need to zoom back in. Okay. Now, that's kind of an interesting picture as well. Interesting function. Let's get some interesting things to happen in here. But what happens far away? Okay. So basically, what should happen close to zero? Well, what happens far from zero is it looks more like just 3x squared over 2x cubed. And as we'll see, that actually goes to zero. Okay, far from zero. So take the limit as x goes to infinity or negative infinity, both those actually go to zero. We can't see it as much here, but once again, if we zoom out quite a bit, you see as the x coordinate gets large, the y coordinate gets really small. And the same thing over here, as x coordinate gets large in the negative direction, the y coordinate also gets really small. Okay. Now, let's go back and take a look. So let's go back to our diagram. So what I'm going to say, a few things, is that so that behavior, it acts more like this. Okay, so let's look at this example as an example. All right. Here we're looking at rational functions. Okay, and the example I want to do then is this. So 3x squared minus 5x minus 2 over 2x cubed. Okay, now once again, we're saying far from 0, this looks like, and also let's call this f of x. This looks like our f of x is approximately, remember these squiggly equal signs means approximately. This looks like f of x looks more like just 3x squared over 2x cubed. And basically cancel things out, that basically, well, I shouldn't even worry about canceling it out. But if you notice, as I say right here in this next part, is that anytime the degree in the denominator is larger than the degree in the numerator, this whole thing goes to 0. Okay? So then, well, here, I'll say so. Think about the limits, as we just saw. The limit as x goes to infinity is equal to 0. I should say f of x. And also the limit as x goes to negative infinity of f of x is also equal to 0. So that's true. Anytime the degree, the highest power in the denominator, is larger than the highest power in the numerator. That happens every time. Okay? Now, let's change this around just a bit. What if we make this bottom degree also 2? So number 2, a very similar function, 3x squared minus 5x minus 2 over 2x squared. Let's see what happens here. As you expect, we're going to have some kind of asymptote at 0, most likely, because x can't be 0, vertical asymptote. But here we're just focusing on what happens far from 0. Okay? So once again, far from 0, once again, this is our f of x. And one more thing I'll say up here, then if we cancel out our x's, we have 3 over 2 the x, and you imagine that will go to 0. That's like 1 over x. That's going to go to 0 the further we get from x. Okay, far from 0, this looks like I'm just going to approximately squiggly lines. Looks like it's more like 3x squared over 2x squared. But you cancel out the x's, that looks like 3 halves. Okay, so it actually should approach a constant. Okay, let's see if it does. Let's go back to Desmos. Okay, now when I do this, also it's going to change how it looks close to 0 as well, most likely. Just change this to 2. Yeah, so it actually changes the function. It's kind of an interesting looking function. In this case, this is an example where once again we said it should have an asymptote at 0. In this case, if you approach 0 from the left or the right, they both approach negative infinity. But let's see what happens. So far from 0, there are 3 halves about 1.5. And so, yeah, as we go further and further out in x, we're getting closer and closer to 1.5. As we go further from x in the negative direction, we're also reducing from above, but also getting closer and closer to 1.5. Okay, so the limit of that, the thing about the limits, so the limit as x goes to infinity of f of x to infinity is just going to be 3 halves. Remember, 3 halves is approximately 1, or not approximately, is equal to 1.5. And that's the same as a limit as x goes to negative infinity is the same, also goes to 3.1.5. 5 or 3 over 2. Okay, then last one. What happens if we make our denominator, degree or power of our denominator larger than the degree of the numerator? Let's do that and see what happens. Once again, up here we have 3x squared minus 5x minus 2 over, let's call this 2x cubed. So this time, the degree up there is larger. And this is our f of x. Okay. Once again, far from 0. This looks like, if we just take the dominating terms, it's like 3x squared over 2x. Oops, I'm sorry, it should be x cubed. It should be x. Sorry. Yeah, so just 2x. If I cancel out the x's here, that's going to be 3 halves x. Okay. So here, as you imagine, as you expect, if x gets larger as you go toward infinity or negative infinity, x is going to keep getting larger itself. So the limit as x goes to infinity of f of x, okay, if it looks like 3 halves x, as x goes to infinity, this whole thing is also going to go to positive infinity. And then the limit as x goes to negative infinity, in this case of f of x, we go toward negative infinity because x is going to be negative. Let's take a look at the graph and see that. Okay, so once again, just change this, make this just x. Oh, oh, there we go. Okay. All right, as you can see, it's going um, toward infinity and negative infinity. But also something interesting happens. Let's compare that. Let's actually, we said it looks like 3 halves x. Let's actually graph that as well. So 3 halves x. And what happens is that as we go further and further from 0, it looks more and more like that straight line, 3 halves x. That's what's called a slant asymptote or an oblique asymptote. Okay, so that's the last part here, last thing I mentioned. So if your degree in the numerator is larger than the degree in the denominator, if m is less than n, then it always either goes to infinity or negative infinity. But if n minus m is 1, if the degree in the numerator is 1 more than the degree in the denominator, you have what's called a slant asymptote. So we have a slant asymptote or oblique asymptote. Or let me say, instead of at, let me say of y equals 3 halves x. Okay, so that's the idea of, so what we've seen then so far is we've seen vertical asymptotes where your denominator is 0. We saw horizontal asymptotes where if you either the degree of the numerator is either less than the denominator or the same as the degree of the denominator. And then anytime the degree of the numerator is larger than the degree of the denominator, it's one more. And it always goes, that one always either goes to infinity or negative infinity. But if it's just one more, if n is just one more than m, we can have a slant asymptote, which is a straight line. Okay, let's look at one more example. And this example is going to be something that's not actually a rational function, but it's similar and it's kind of interesting. So this time let's do this. Let's say our f of x is equal to the square root of 3x squared minus 5x minus 2. So putting that same polynomial just under a square root, make this over x. Okay. Now, one more time, this is not a rational function technically because a numerator is no longer a polynomial with a square root. But what happens is have a similar behavior. Okay. A similar behavior far from 0. Okay, so far from 0, once again, the higher powers will dominate. Okay, this looks like f of x to be approximately, it's going to squiggly equal signs, square root of 3x squared over x. Okay, now if you think about the square root, remember some of your rules of square roots, we can break this up in the square root of 3 and then the square root of x squared. X, and basically as long as x is positive, this becomes the square root of 3. Then we have x over x, which is just the square root of 3. Okay. Now, so let's take a look at the graph. And as we'll see, depending on whether x is positive or negative, this can be positive or negative. Let's graph this one. Remember, always use the graph to help you out. That's going to help you out a lot anytime you're graphing these functions. So let's actually just turn these off. And then I'm just going to copy this one. Okay, I'm going to do a square root. Just type SQRT, then paste. Then let's divide this whole thing by x. Okay, I actually need to zoom in. You can't see anything yet, but as we'll see, this is what we get. Now, one thing's kind of interesting here, is there's a gap in between. And actually, that's where that gap is where our polynomial 3x squared minus 5x minus 2 is actually negative. Of course, you can't take the square root of a negative number. I can prove that by actually plot this and graph it. Actually see the blue line is now just a polynomial where it's below 0, where it's negative, lines up with that perfectly. Okay. But once again, as we saw, this should look kind of like square root of 3, or actually maybe the negative square root of 3. Let's approximate both of those. So let's draw these horizontal lines. Y equals square root of 3, and which is about approximately 1.73. And then let's do the negative one. Okay, y equals negative square root of 3. Okay, and as we'll see, if you zoom out on this, you'll see those approach those extremely well. Okay, so those are horizontal asymptotes. There actually have 2 in this case. Okay, and so they both approach the square root of 3. So let's actually write that. So as this function goes to infinity, positive infinity, it goes to positive square root of 3. If it goes to negative infinity, it goes to negative square root of 3, or about approximately 1.73. Okay, so let's put that down. So limit as of f of x as x goes to positive infinity is equal to the square root of 3, which is approximately 1.73. And then the limit as x goes to negative infinity of f of x goes to negative square root of 3, which is approximately negative 1.73. Okay, so let's review what we've done today. So we introduced the idea of limits and infinity. So basically, limits that can equal infinity. Okay, we have a vertical asymptote, for example, when you approach a specific number, limits can go to infinity, or also the limits go to infinity of rational functions, as we've seen. They will in some way. Then we actually have limits going toward infinity, whether they go up to positive or negative infinity. And we sought to evaluate those. And once again, graph these, make sure you're graphing as your friend. That will help you to understand what it looks like, and also gives you some idea of how many asymptotes you should have. Because remember, you have an asymptote wherever the denominator is 0, but just because the denominator is 0 doesn't necessarily guarantee an asymptote there. It's either an asymptote or a hole in the graph. Also looked at other kinds of asymptotes, horizontal and slant asymptotes, and looked at behavior of rational functions far from 0. Thank you. Have a good day.